Go ahead and start. So I put like an agenda kind of thing. I have a lot to go over, but I won't keep you too long. So I'm going to go over nomenclature of alcohols, and these are the three reactions of alcohols you'll need to know. So the reaction of alcohols and alkali metals, acid catalyzed dehydration of alcohols, and Lucas reactions. And then I'll go over some stuff about phenols.
How do you retain all this information?
What do you mean? Like,
our class every day is a pop quiz for you.
Yeah, it really is. Sometimes I don't. Well, see, your class is like the second trial, and he does the same thing to me in the 9 a.m. So I'll get it right like most of the time in the 9 a.m., but sometimes I won't, and he'll correct me. So then by the time he asks me at 11 a.m., then I know. So that's, yeah. I don't always get those questions right.
I was really curious. I'm like, she remembers everything.
Yeah, no, I don't. I remember a decent amount. And he never tells me when he's going to do that. I'm like, I'll just be like, Lydia, can you explain that part? I'm like, I guess. Yeah, I can. He's funny. Okay. So, nomenclature of alcohols. It's been a hot minute since we did this. It's pretty standard, though. The first step is to number the chain, identify the longest chain, and it has to include the OH group on the chain. So even if there's a longer chain that just has carbons, you can't use it because it has to have the OH group. You'll number the chain with the OH group holding the smallest possible number. So that's your priority group, is the OH group. So you want that to have the lowest number. And then you'll just designate positions, names for all your side groups, and a suffix for alcohols is ANOL. So we could practice this one. The first step is just, again, longest carbon chain. So I can have one, let me get my pen. I can have 1, 2, 3. You have to make sure that's the longest one. So I could count here, 1, 2, 3, 1, 2, 3. It's the same. So, and in this case, it doesn't matter which end I start counting from because the OH group is on the middle one. So whichever way I count, it'll still be on 2. I have 1, 2, 3. So that makes my side group here, and then this is my functional group. So this is a methyl group, right? And that's on C2. So my IUPAC name will be 2-methyl 2-propanol because my carbon chain has 3 carbons. So prop is my, what is that called?
Your parent chain.
No, the other word for suffix, what is that called?
Your prefix.
Prefix, yes. And then ANOL is my suffix. And then the common name for this is tertiary butyl alcohol because this OH group is connected to a tertiary butyl group. Does that make sense? So you'll need to know both the IUPAC name and the common name for this one. That says IUPAC, but okay. So I have one more example. Again, first step is just identify the longest chain. So I have 1, 2, 3, 4, 5. Just make sure that that's the longest chain. 1, 2, 3, 4. Okay. So I know that this is my longest chain, and it includes that OH group. So which side am I going to start counting on?
Right.
Right. Yeah, because this end is closest to that OH group. Okay. So now just name and designate side groups. This is my only side group. This is a methyl group again, and that's on C3. Okay. So this will be 3-methyl 2-pentanol because my OH group is on C2. Does that make sense?
Yeah.
Okay.
If you have a double bond or you have multiple groups that say you start counting from me, how do you know which one you start counting from? If you don't know this again.
I would say if you had like a double bond here, I would say that you would start with whichever like double bond or functional group would give the lowest number.
I know what you mean.
I don't know though. Or it could be like what's the most important for its chemical properties that you would have like the highest priority group. So like, I don't know, if this compound had like more properties of an alcohol than an alkene. I don't really know though. So, sorry. That might be a doctor's son question.
And he'll say, Lydia?
And I'll be like, Lydia, can you answer that? I'm like, no, I can't. Okay. So this is the first reaction of alcohols that you'll need to know. You don't need to know the mechanism for this, but it's pretty straightforward. So alcohols reacted with group 1 alkali metals on your periodic table, which the only ones you'll see are sodium, lithium, and potassium. That produces an alkoxide. Okay, so the covalent OH bond in your alcohol is more or less just replaced with an ionic bond between the oxygen and the metal. Okay, so the general equation is ROH, which is just any kind of alcohol, plus a metal yields an alkoxide, which the oxygen will hold a negative charge and the metal will hold a positive charge. And then plus 1/2 H2. So only one hydrogen comes off, but you need to write it like this because hydrogen is not stable by itself unless it's in H2. So that's why you write it like this, even though it's just one hydrogen. So this example up here, this is methanol, right? And when I react methanol with lithium, I just replace that hydrogen with the lithium. And this OH bond here is a covalent bond, but with the metal, the lithium bond is ionic. So the charges are just here to emphasize that it's an ionic bond and not a covalent bond anymore. So your oxygen will be negatively charged and your lithium will be positively charged. And then you'll have 1/2 H2, which is just one hydrogen. Okay. So we can do this one. Again, it's very straightforward, just the exact same thing. So this is that alcohol we just named, right? I should pick a different color. We have tertiary butyl alcohol. React with sodium. Okay, so that sodium is just going to replace that hydrogen there. And I'm going to have a negatively charged oxygen, positively charged sodium. And then one hydrogen again. Okay, and these are alkoxides. We good on that? Okay. So again, you won't need to know the mechanism for that, but he'll probably just like give you something like this on a test maybe and be like, what does this make? And you'll just be expected to know that alcohols and alkali metals make an alkoxide. Okay, so the next reaction of alcohols you need to know is dehydration. So alcohols can undergo dehydration, which just means removal of water in the presence of a strong acid. So it can occur with primary, secondary, and tertiary alcohols, but the mechanism is different for primary alcohols, which I'll go over in just a second. It does require heating as well as the catalyst of a strong acid. Primary alcohols require the most heating. I think the example the other day was like 180 degrees Celsius. Requires more heating than secondary alcohols. I think that was like 80, and then tertiary was like 60 degrees Celsius. Okay, so we can go over the example for this. So just the general equation is you just take the OH group off, and then you take a hydrogen off of the adjacent carbon, and then you form a double bond between those two carbons. That's an H up there. And you have water. Okay. So first step of your mechanism is always protonation of the OH group. Because this OH group, as it is now, is a poor leaving group, which just means that this CO bond is too strong for it to break easily. Okay, but we want to take it off, so we want that bond to weaken, and we want it to be able to break off. Okay, so I have to catalyze with an acid for this step, for the protonation step. Okay, and if you don't remember, sulfuric acid structure is this right here. Okay.
Do you think you would ever put a weak acid up there? We have to be like, does not react.
No, I don't think so. He probably won't ever actually give you any other acid but sulfuric. So he might ask you like further reaction conditions, and you'll just have to say heat in the presence of an acid or something like that, maybe. Okay, so this oxygen here has two lone pairs of electrons. Okay, so I want to protonate. So these lone pair electrons are going to come attack this hydrogen, and then this OH bond is going to break. Okay, so if you remember, I said that the mechanism for primary alcohol is different. That's because of this step. So in the secondary and tertiary alcohol mechanism, this water breaks off because it's a good leaving group now, and then we form a carbocation. But this would be a primary carbocation, which can't actually be formed. So instead of that part happening in two steps, all of it happens all at once. Okay, so this CO bond breaks because this water is a good leaving group. So water comes off, and at the same time, this anion that we made here comes and attacks the adjacent carbon, or one of the hydrogens on the adjacent carbon. So it'll take this hydrogen off, and then these CH bonding electrons will go in between those two carbons to make a double bond. And this all happens in one step for primary alcohols. So I'm left with this and water, and then I reform sulfuric acid because I use it as the catalyst, which means I have to reform it. Does that make sense? Okay. So now we can move on to dehydration of a tertiary alcohol, which is about the same, but like I said, that one step, instead of happening all in one step, it'll happen in 2 steps now. Okay, so my product will be this, right? Because I'm going to take this oxygen off and I'm going to take one of these hydrogens off. It doesn't matter which one because they're equivalent. So I'll take one of those hydrogens off. I guess how I drew it, I took one of these off. And then you'll form a double bond between those two. So this is actually a bit easier to look at. And then I'll have water come off. Okay. So our mechanism, first step is still the same. I'm going to protonate that OH group because I want to convert it to a good leaving group because it's a poor leaving group right now. So these lone pair electrons are going to come, attack that hydrogen, and this bond is going to break. And then I have OH2 formed and then a positive charge on that oxygen because it has too many bonds. Okay. And then I have this anion formed. Okay. So from here, I don't have to do it all in one step because this will form a tertiary carbocation, which can actually be formed. So this CO bond will break. Those bonding electrons will go to that positively charged oxygen, and I'm going to lose water. So I have a positive charge formed on that carbon. I have a tertiary carbocation. I'd probably emphasize that hydrogen. And then again, I still have this anion. Okay, so this anion is going to come take one of those hydrogens on either of those carbons, it doesn't matter which one. And then the bonding electrons from that carbon and hydrogen bond are going to go in between the 2 carbons and make a double bond.
That's why I had to move.
Why even move it?
That's why I had
Oh yeah, that whole table sucks. That's where I sit in physics and I like can't move without it just
Well, like I
creaking.
feel bad because you're like trying to like do stuff
No,
over
it's
there,
fine.
just like clicking and.
Yeah, I can't even move in physics without it making noise.
Yeah, me and Noah sit in this one. I thought it was gonna collapse one day.
Yeah, it like moves every time you even move a step. Okay, but anyway, this is my product, and then I form water, and I reform sulfuric acid. So the only difference between primary and then secondary and tertiary alcohols in this mechanism is primary alcohols do these 2 things in 1 step, and then the secondary and tertiary do it in 2. Okay, so the last one for alcohols is Lucas reactions. Okay, so alcohols can react with halogens, so chlorine, bromine, iodine, to form alkyl halides and water. And you don't have to catalyze these reactions or heat them unless it's a primary alcohol, which those reactions are not very favorable and not very common. I don't think he'll ever give you one of those, maybe. I could be wrong, but I doubt it. So tertiary alcohols will react faster than secondary alcohols, which has to do with carbocations. You guys remember all that. And then secondary alcohols will react faster than primary alcohols. So the rate determining step in these reactions is the formation of the carbocation, which is the slow step. And the general equation is you have ROH, so your alcohol. It's going to mix with HX, which could be HCl, HBr, HI, to form an alkyl halide, RX, and water. Okay, so we can practice these. Okay, so these, in essence, are substitution reactions. Okay, so you're just substituting the OH group with your halogen, and then you form water. Simple enough, right? Okay, so for the mechanism, the first step is, again, you want to protonate that OH group because you want to take it off, and you can't take it off when it's just OH. Okay, so I have these two lone pair of electrons here. If I could draw them, oh, for Pete's sake. Okay. So one of those is going to come attack this hydrogen, and this HBr bond is going to break. Okay, so I added that hydrogen to that oxygen. So now my oxygen has a positive charge, which means it's a good leaving group now. This will break, and I also have my bromine anion right there. So when that water breaks off, I have a carbocation formed, and this would be secondary. And then I have my bromine anion is just going to come attack that positively charged carbon. Just put my two there. Okay. So these ones are a bit simpler. The first step is still the same. You protonate that OH group, take water off, you form a carbocation, and then just your halogen anion is going to attack that carbocation. Does that make sense? Okay. So we can do one more of those. Again, in essence, these are just substitution reactions. So this is a tertiary alcohol. It's 2-methyl-2-butanol. Do we see where I got that name? Okay. Okay, so I'm just going to replace that OH group with my halogen, and I'm going to form water. Okay. So mechanism is still the same. My two lone pairs of electrons on oxygen combine with HI. It's going to attack that hydrogen, and then this HI bond is going to break, and those are going to go to my iodine. Okay, so I added that hydrogen to that oxygen, which means it now has a positive charge. So now I can take it off. That CO bond is going to break, and the bonding electrons are going to go to that positively charged oxygen. And I also have my anion. Okay, so now I form my carbocation, and this would be tertiary, which means that this would react faster than the last reaction we did, because this has a tertiary carbocation when the one before only had secondary. Okay, so now that I formed my carbocation, I still have my anion, and this is going to attack that positively charged carbon, and I'll form my product. And I also have water. Do those make sense? Yeah, these are a bit simpler than the dehydration reactions. Okay, so that was it for alcohols, at least for now. The next thing we talked about was phenols. So the general kind of formula for phenols is C6H5OH. That's called phenol, but phenol is also a class of compounds. So you can have like phenol derivatives. So this is phenol here. And it's a weak acid because if you remember, this aromatic ring has something called the conjugation effect. Okay, so this oxygen has lone pairs of electrons. So these lone pairs of electrons can actually delocalize to this ring, because it already has that conjugated pi system. So when these lone pair of electrons actually delocalize to the ring, it takes electron density from the oxygen, which weakens that OH bond. Okay, so that's why it's a weak acid. Okay, so down here you can see in water it does slightly dissociate. Okay, so this hydrogen can come off as a hydrogen ion some of the time. It partially dissociates, hence weak acid. So the important thing to remember about phenols is it's a weak acid, and the OH group for phenols is connected to an sp2 hybridized carbon, while in alcohols the OH group is connected to an sp3 hybridized carbon. Okay, so you don't want to mix up the two, because phenols are not alcohols and alcohols are not acidic. So this does not happen to alcohols. And remember, this is just another way to show an aromatic ring is just with the ring in the middle. Okay, so up here we can talk about phenoxides, which are similar to alkoxides, but do not get them mixed up. So how to make a phenoxide: you take phenol and react it with a strong base, so sodium hydroxide, and from there you can replace that hydrogen with the sodium, and you can also form water. Okay, and that reaction does not happen with alcohols. It only happens with phenols because they're slightly acidic, so they can have acid-base reactions. Remember from Chem 1, acid-base reactions form a salt, which just means an ionic compound, which is what this is, and water. Okay, so this is essentially an acid-base reaction to form a phenoxide. But remember earlier, this does not happen with alcohols because alcohols are not acidic, so they cannot have acid-base reactions. And to make an alkoxide, you just react with sodium and not sodium hydroxide. So they do look very similar, but be careful not to mix these up, because he'll be picky about that, I'm assuming. And that is all, my friends.
Do all aromatic rings not make alcohols?
What do you mean?
Like for phenol, it is not an alcohol, and alcohols are not acidic. Is that true for all of the aromatic rings we're working with?
Yes. So if the OH group is connected to anything that's sp2 hybridized, it is not an alcohol. So it doesn't have to just be this aromatic ring. If it's connected to anything that's an sp2, now depending on what it's connected to, it might not be considered a phenol.
Right.
But if it's connected to anything that's not sp3 hybridized, then it's not an alcohol.
That was
Anybody else?
All three of us.
Well, that's all I got, my friends.
Thank you, Lydia.
are you able to send this one and the last one out to us?
Mm-hmm. The PowerPoints?
Yes.
Yeah, I was just thinking